giving me the opportunity to speak here. So this is a joint work with Camilo Hernandez, which is my PhD student at the Universidad de los Andes, the math department. So I'm going to talk about the Finetti's problem, the Finetti's optimal dividend problem, but with a constraint in the time of ruin. So let me start with the outline. So first, I'm going to define what is the Finetti's problem, which is a very old problem from the actuarial sciences. Then I'm going to tell you what is the problem that I'm trying to solve, which has a constraint on the time of ruin. I'm going to talk about the dual problem, a few words about the exponential claim case, which has been already published, and an extension that we already have for spectrally negative Levy processes, numerical examples, and some extensions and future work. So first of all, what is the Finetti's problem? So we have an agent, let's say an insurance company. So this insurance company has a reserve process that I call X. For example, something like this. And we have claims that are modeled like negative jumps. For example, like these things. So we have this reserve process X. And we have a dividend process D, which is the cumulative payments that the company makes through the time. This is an adapted, non-negative, non-decreasing Cadillac process, starting at 0, adapted to the filtration generated by X. And if we have X minus D, we have the surplus process. And we don't allow the dividend process to lead to ruin the reserve process. So that's this condition. So we have theta, the set of strategies that don't allow ruin, don't lead to ruin. So the objective function is to maximize the flow of discounted dividend payments throughout the time until the time of ruin, which is this tau d that depends on the strategy. I'm using here Q because I'm going to use Q scale functions like Daniel did before. So the Finetti's problem is just find what is the best strategy for dividend payments. And this is very old. And for some processes, there is a book by Schmidtly that summarizes all the techniques used to solve this problem. And later, we have this work by Loffen that extend to the spectrally negative Levy process that I'm going to talk about later. So what is the motivation of imposing this constraint? There is a trade-off between the stability of the company and the profitability of the company. If we want to minimize, for example, the ruin probability, then that will lead that we don't pay any dividend. But if we maximize the dividends payment, then we will have a certain ruin. So the idea is to balance this trade-off, imposing a constraint. Some related work in this direction is this work by Paulsen, Tauhausen, and Albuquerque. This is going to be important for us. Also Loffen and Renault. So the actual problem that we want to solve is this. We want to maximize the present value of the dividend payments subject to this constraint. So the idea of this constraint is that maybe I want the company to live at least a certain amount of time. So this is the meaning of this T. So this is the problem that we want to solve. So the idea is to use a Lagrangian relaxation to take the constraint into the objective function with a Lagrangian multiplier. So we have that the original problem is going to be the sup, the inf of this Lagrangian function. That's easy. And we have the dual problem, which is just changing inf with sup. We always have this inequality already. So the goal is to prove that there is no duality gap, that we actually have zero duality gap. So we're going to focus on solving this problem, which is the auxiliary problem, which is now a standard control problem. So we want to find how is this is this problem, so what is the solution of this problem, and trying to use it to prove that there is no duality gap for our original problem. So we started with a simple scenario, which is the case of the Cranberg-Lumber model, which is basically a compound Poisson process with a positive drift with exponential claims. So that's the Cranberg-Lumber model. And we were able to prove that there is no duality gap. And in fact, the value of our problem is just the infimum over all Lagrange multipliers of this auxiliary problem. And the key point there was the simple strategy that Daniel was talking about earlier. So we have barrier strategy are optimal for this problem. So we thought that maybe in a more general context, we have also barrier strategy, and that's the context of spectrally negative Levy processes. So this is basically what Daniel had earlier. So a spectrally negative process is a Levy process which measure is supported only on the negative side and has no monotone paths, almost surely. So we are not allowing like subordinators. We have the Laplace exponent, and we also have the Q scale function that Daniel was talking earlier. So I think I'm going to skip that. And we also have these sig functions which are defined in terms of the Q scale functions. So why? Because, as Daniel mentioned, so we have the theory of excursion theory, and we have these reflected processes. So if I choose a barrier strategy level B, then the dividend process is going to be just the maximum of B and the running maximum of X minus B. So the surplus process with this strategy is going to be this, and this is basically just reflection in this barrier. So so we have a lot of theory for this reflection process. And so, for example, we can write the objective function in terms of the Q scale function. That's one thing. And the other thing is that we can also write, so we have this property, this identity from Abram and co-authors that we can use to write the left-hand side of our constraint in terms also of Q scale functions. So if we combine all this together, love indeed. So we have that if I choose a barrier strategy at level B, then the Lagrangian function for that strategy is just this in terms, and everything is in terms of the Q scale function. And if I want to optimize over this set of strategies, I just need to optimize over B, which only appears here. So basically, that's how you get what is the best barrier strategy, and then you use a verification lemma to prove that this is actually the optimal strategy. So we take this part that I'm calling here zeta lambda, and you just take the maximum of this. And for the case when the Levy measure is complete monotone density, has a complete monotone density, like most of the cases, like for example, alpha stable process has this property. So we have that this function has a unique maximum, and that's going to be the optimal strategy. So this is the definition of a complete monotone function, and some examples. So Laufen proved what is the strategy for the auxiliary problem. So under some conditions, the optimal strategy is take the money and run, which is just paid everything out in dividends. Otherwise, there is going to be an optimal level given by this formula, or the maximum of this is going to be. So that is useful for us because then we have a way to, given a B in this set, this B star is going to be the level of the definitist problem without any constraint, this B0 star. So if we have a B here, then I can map this B to a lambda so that the level B is optimal for the auxiliary problem with that lambda. And that basically what allows us to have a certificate for optimality. Then we have this B star, this lambda star, and we can prove, for example, complementarity slackness condition. And that's what we did. And basically, the proof, so we have the analog theorem for this case, that we don't have duality gap, and the value function of this constraint problem is just the infimum over lambdas over the auxiliary problem. And the idea is, so we define this function C, which is just the left-hand side of our constraint. And we try to find certificates for strong duality, B star and lambda star. And we divide in 4 cases. So if I take an x, so note that here x is fixed. So I start with an initial capital X. And I also have a t, which is the parameter of the right-hand side of the constraint. So given x and t, I can find what is x here, what is kt, and find the point where these 2 lines intersect. For example, if they intersect in this region, that means that the constraint is not active. So the strategy with that constraint is optimal. If they are in this region, that means that there exists a unique b, such that this function phi sub b, which is something like this, goes through that point. That means that the constraint is active. If I'm in this region, that means that the problem is infeasible, because the initial capital is too small, and the constraint is too hard to fulfill. So if we are in this region, the problem is infeasible. And if we are in this borderline, then we have that the optimal strategy is do nothing, but we are still feasible. So analyzing all these 4 cases, we have the proof for the theorem. So as a numerical example, I'm going to take the x as a Levy process with gamma, the positive drift 10, for example, a diffusion term 0.1, and this is going to be the Levy measure, which is basically this is telling us this is a 0.8 stable process with diffusion. And for that case, so this is how the function phi c sub b behaves. So for example, if I'm in this point, this is the blue line is the line corresponding to the level without constraint. So if I'm in this point, the constraint is not active. If I'm in this point, so there is a unique line here that goes through this point. So that's the B star that is the optimal strategy. So these are the cases. The other cases, I don't show it. These are the values for the auxiliary problem for these cases. So in this case, when the constraint is not active, so the minimum is at lambda 0, so that means that the constraint is not active. If in the other case, this function b lambda is always a convex function on lambda because it's the dual function. So we have a unique minimum here in this case. And these are the value functions for different right-hand side. So the blue line is the value function without the constraint. If t is a little bit bigger, then so this is going to be the value function. And here, for example, this is not that the value function is 0. It is in this region the problem is infeasible. So so only makes sense for x to be only from this point on to have a finite solution. So some extensions we are working now in the dual model, in which in this case the process is a spectrally positive Levy process. So we have a negative drift and jumps upwards. We can try to do something similar when we have a fixed transaction cost. In this case, it's proven that the optimal strategy is a band strategy. So if we are below some level, we take the if we are below some, if we are in some level, we take the dividends down. But then I don't have only one parameter. I have 2 parameters, 2 levels, two values of b. So then we have to do some work to prove a similar theorem, and also try to extend to more maybe realistic constraint like this. This would be a constraint like more natural than we imposed, or something like this kind, which seems harder to deal with. So these are some references. This is where many of the identities for the spectral, the QSCAL functions, you can find many of these identities. And this is the paper where we published the results for the exponential claims. And I think that's it. Thank you.
Questions or remarks? So you mentioned some extensions with some constraints, probability constraints, or constraints or on expectation. Can you also consider constraints almost surely, or is it something?
That could be also a possibility.
Okay. 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 Other questions? If not, thank you again for the presentation, and we can move to the last talk.